Very much. I'd like to begin by thanking the organizer for such a wonderful conference, and it's a great pleasure to be able to speak here. So the title of my talk is Supersymmetric boundary condition called 2 series. This is a joint work with Satoshi Yamaguchi at Osaka University. So let me begin by the introduction. So what do we study? So same as the previous talk, so I'd like to talk about the 3D n equal 2 supersymmetric series with boundary. And more precisely, the space-time is R11 times R plus, and R11 is labeled x0 and x1, and R plus is labeled by x2. So we think of flat half space. And the problem is, how can we preserve supersymmetry on the boundary? So as you know, so supersymmetry is related to translation. So if we have the boundary, so we have to break the supersymmetry. But in some cases, we can preserve a fraction of supersymmetry. So that is a supersymmetric boundary condition. And originally, we have 4 supercharges in 3-dimensional n equal 2 series. So I'd like to discuss the 2 supercharges with preserved conditions. That is a half BBS condition. So why it is interesting? So I will give you 3 motivations here. So the first motivation is related to the Brane description in terms of membrane. And the second motivation is the 3D dualities in which we have the boundary. So we have many dualities in symmetries in 3 dimensions, and we consider the boundary case. And the third motivation is extension of AGT and the DGG relation. So I will briefly explain about these motivations. About first motivation, I will let me remind you the story in 2-dimensional 2,2 sigma model. So this in this case, so we can interpret the 2 dimension as a world seat of string. And the target space is ambient space of string. So string embedded in this target space. And if we have the boundary, so we can impose supersymmetric boundary condition on this. And this condition specifies some configuration of fields. So we can interpret this as Brane on which the string can end. So this is good, so useful to investigate the mirror symmetry. And so in 2000, Hori-Ikuba Wafa papers discussed this mirror symmetry. So namely, the strings can prove geometry. So it might be interesting problem. What about membrane cases? So namely 3D sigma model. So I will briefly talk about a piece of our results later. And the second motivation is 3D dualities with boundary. So we have many dualities or symmetries, like a mirror symmetry, Zyberg-like duality. So what happens if we have the boundary? And so similar analysis was studied in 4D n equal 4 by Amir series. That is the action of S duality on supersymmetric boundary condition. And so in that analysis, so 4D n equal 4, so S duality is related to 3D n equal 4 mirror symmetry. So it has a possibility to connect with 2-dimensional 1,1, 2,0 mirror symmetry. But I cannot reach the results. So here, so I will talk about the some comments in Abelian duality and mirror symmetry. So the final motivation is the extension of AGT and the DGG relation. So actually, this is a reason why we think of n equal 2 cases. So let's start with M5 range 6D 2,0 theory. So we can divide 2 parts, D plus 6 minus D. And the other part is description of supersymmetric gauge series, and the other part is so some manifold. In the equal 4 case, we have the many example of this relation, so Zyberg-Witten series and AGT relation. In the equal 3 case, recently, so Kolbach-Cody buffer, the similar analysis for Zyberg-Witten series and DGG relation is the extension of AGT relation, so labeled by C manifold. But my extension means, so this, how about D equal 2 cases? But so far as I know, so no examples, we have no examples. So how to study? So here, so I will suggest the 2-dimensional supersymmetric domain model construction in 3D n equal 2 series is useful.
No, we do have examples.
Already?
No. There are all sorts of examples of them, five mains wrapped on 4 cycles. Where elliptic genera are related to Buffer-Witten partition functions.
Okay, I see. Thank you. Okay, so my suggestion is, we think of the domain wall in 3D n equal 2 series, but before that we have 3D n equal 2 series. And by using a DG relation, we can connect to 3 manifold and input the domain wall. Then we can construct some 4 manifolds, has a boundary, has a 3 manifold as a boundary. But here we use a folding trick. So then we can make into this system. So this system is defined on a half plane, half space, and we have the supersymmetric boundary condition in this system. So in this sense, supersymmetric domain wall is equivalent to supersymmetric boundary condition. So these are the motivations. So let us explain about the analysis for supersymmetric boundary condition. So the strategy is very simple. So we need 2 information. So one is Lagrangian and the supersymmetric transformation. So given these, we can calculate supercurrent. And then, so the condition that preserves supersymmetry on the boundary is we focus on the normal direction, normal component of supercurrent. That is a vanishing condition or normal contribution of supercurrent. So the condition is given by this equation. So this is a supersymmetric boundary condition. So the problem is, what is the solution of this equation? It is a very simple question. But to solve the equation, we notice that we have 2 types of supersymmetric boundary condition. So that is classified by the action of gamma 2 matrix on epsilon. Epsilon is a supersymmetric SUSY generator. So we have 2 types of boundary condition. And each of these has can preserve supersymmetry 1, 1 type or 2, 0 type.
Is 1, 1 going to be enhanced to 2, 2?
Yes, exactly. No, actually, I don't know. But the 2, 0 case, we have the decomposition of 2, 2 decomposed into 2, 0.
Because normally if the target is scalar, then it's 2, 2 automatically.
Yes. But I don't know, understand in the case of 1, 1 case. Yes. So the problem is, what configuration can be allowed for each case is A-type and B-type. So this is here is the outline of remaining my talk. So section 1, I'd like to talk about the n equal 2 random Ginzburg model. And section 2, I'd like to tell you n equal 2 pure Maxwell theory and Abelian duality. And time permitting, I will tell you n equal 2 SQED and mirror symmetry. And finally, I conclude. So section 1, so the Lagrangian of the Ginzburg model is given by this. So K is a Kähler potential, and W is a superpotential. So this theory can be identified with a 3D sigma model with target space, any dimensional target space. So the dimension is a complex dimension. And similarly, so we think of 3D is some world volume of membrane, and target space is our ambient space of membrane. And we impose the supersymmetric boundary condition. Then we have some subspace spanned by the supersymmetric boundary condition. And that is identified with Brane in this way. And we have 2 types of boundary condition. So we give the name A Brane, B Brane for each cases. And from this supersymmetric transformation, and we can calculate supercurrent and supersymmetric boundary condition. So the problem is to solve this equation. So we impose the answers to solve the equation. So that is the action of gamma 2 matrix on psi, the fermionic fields. Namely, so matrix S and R is given by this form. And we have the solution. We found the solution. So G is the metric of target space. And B and W and U and Z are vectors in target space in terms of fermionic field psi. And from these solutions, and also considering, so taking account the vanishing condition of boundary terms, surface terms, we can conclude that A brane is Lagrangian submanifold, and B brane is homomorphic submanifold. And also superpotential, imaginary part of superpotential is constant on A branes, and superpotential is constant on B brane. And this is same result in two-dimensional 2,2 random Ginzburg model. Okay, so as a section 2, I'd like to tell you the pure Maxwell theory and Abelian duality. So the Lagrangian is given by this. So sigma is a linear multiplet, and F is a gauge field strength, and lambda is a gauge, and sigma is a real scalar field, and D is an auxiliary field. And from these two information, we also calculate supercurrent and a supersymmetric boundary condition. And we also impose the ansatz, the action of gamma 2 matrix on fermionic fields. And we have the solutions. And here, the configuration is written in as a configuration for F field strength and the real scalar field sigma. But noticing that we have the description of dual photon in 3 dimensions, we can rewrite the configuration of F and sigma into rho and sigma. So the configuration of rho and sigma is given by this. So now we can interpret these conditions are directly Neumann hybrid boundary condition. On the other hand, so B1 type and B2 types are identified with a Dirac boundary condition and Neumann boundary condition. Also, we noticing that the Dirac quantization, from Dirac quantization, so dual photon is periodic. So we can draw the picture in rho and sigma plane as a cylinder. So the picture is given by this. So the point is, so A type, the configuration is one-dimensional object, the line. On the other hand, B type, so we have the configuration as a point or two-dimensional object. So that is the result of the supersymmetric boundary condition in Abelian Maxwell theories. So now I discuss the Abelian duality. So this was discussed in 1997, Debois-Horio's paper. And this is kind of so interpreted as a Legendre transformation or a Fourier transformation. So we begin with some functional, this functional. Sigma is an unconstrained superfield, and phi is a chiral superfield. Then we think of the path integral of this functional and try to integrate out phi and phi bar. Then we have some constraint for sigma, and then we can think of this theory as a pure Yuan theory, Maxwell series. On the other hand, we have another possibility to integrate out. So we integrate out sigma. Then we have free chiral matter field theory. So this is sort of dual. So this duality is so Yuan pure gauge theory and free chiral matter theories. And this is called Abelian duality. So what happens for supersymmetric boundary condition in these two dual theories? Okay, here are the results. But these configurations are the results for Yuan pure Maxwell series. And considering this dictionary between two dual theories, so sigma, rho, lambda, lambda bar are the fields for Yuan pure Maxwell, and right-hand side is for the free chiral matter field theory. Then we obtain the same configuration for free chiral matter field theories. And also we can check the A type is a Lagrange submanifold because the configuration is one dimension in a two-dimensional plane. And also B type, so we think of this object as a homomorphic submanifold in two-dimensional plane. So this is a boundary condition of Abelian duality. Okay, so as a section 3, I'd like to tell you the 3D n equal 2 SQED and mirror symmetry. So the Lagrangian is given by this. So we have so this theory is NF equal 1. So we have flavor and also Yuan pure Yuan gauge theory. And the supersymmetric transformation is given by this. And we also calculate supercurrent and supersymmetric boundary condition. And the problem is to solve the equation. But actually, so it seems so far it seems that we have many solutions for this. So for this equation. So here I only pick up one example of this solution. So this is the example of the solution. So B-type solution. So we take the ansatz, the action of gamma 2 matrix on fermionic fields, and the configuration for bosonic fields. So this is phi is a matter fields, and that satisfies the Dirac boundary condition. On the other hand, so the rho and the sigma satisfy Neumann boundary condition. And so this is a moduli space of SQED. So we have Higgs branch and Coulomb branch. Then I try to draw the picture on this plane. So we have the condition for phi and rho and sigma. So we can draw the picture in this way. So this is the result for SQED. And so now let's turn to the discussion of mirror symmetry. So SQED is said to be dual to XYZ model. So the superpotential is given by this cubic term. And so I remind you that the XYZ model is one of the examples of Landau-Ginzburg model. So Landau-Ginzburg model has superpotential, and if we take the superpotential as XYZ, we obtain the XYZ model. In the B model case, the solution of the supersymmetric boundary condition is the superpotential is constant. So we have the solution as z equals 0, and we can draw the picture in this way. So xy equals x equals z equals 0 and z equals x equals 0 branches. And this can be identified B branes in holomorphic submanifold in a target space. So we obtained some dual pairs, but it's kind of conjecture because we have many solutions and we have other possibility to make some dual pairs. So say we have not a good understanding of this dual. Okay, so finally I will conclude this talk. So conclusion, so A-type and B-type, we can preserve supersymmetry on the boundary 2-dimensional 1, 1 or 2, 0. And Landau-Ginzburg model and A-brane can be identified with middle dimensional Lagrange submanifold, and B-brane can be identified with even dimensional holomorphic submanifold. And in pure Maxwell theory case, we can have the dictionary between two theories and exact correspondence between pure Maxwell and free color matter theories in the boundary condition level. But here we have some not good understanding for SQED and boundary condition for in a mirror symmetry level. So, but we can find some mirror pairs in V-type. And these are the future works and applications. So I'm really interested to couple to 2-dimensional boundary degrees of freedom, but I think it's needed to consider in gauge theory. So this is a interesting problem. And also we would like to add the term of Chern-Simon terms and FI terms and no Abelian cases, the curved background cases, curved CDN equal 2 series. And applications is, so as I said, so 2D, 4D relations or 2D systems, dualities, and Brane construction. That's the end of my talk. Thank you.
Time for questions.
Do you have any hints about what branes might look like if you added degrees of freedom on the boundary, or do you know what kinds of degrees of freedom?
Actually, so in last week I was suggested by Sergey that the 2-dimensional 2, 2 actually, if we restrict on V-type, So we have 2, 0 supersymmetry on the boundary. And 2, 2 merge space can be decomposed into 2, 0 merge spread. So we have chiral merge spread and Fermi merge spread. So in that level, we have some good interpretation of B branes as there are some holomorphic bundle structure. So yeah, in B case, we have some good understanding, but I don't know how about in 1, type or.
So let's thank Tadashi again.
Thank you.